Okay, so now we're going to go ahead and we're going to look at chapter 9. So we've spent a lot of time on linear equations first semester. Second semester, we started talking about quadratics, so our parabolas, our x squared things. And now what we're going to look at is we're going to look at exponential functions. So the first thing we're going to look at when it comes to exponential functions is what we call geometric sequences. And so geometric sequences are representing exponential functions. So what we have is we have several different things to deal with. We have what we call a term number, which is as I list out numbers. So if it's the second number listed out, it is term number 2. If it is the fifth number listed out, it is term number 5. And then the number itself is known as the term. So when I'm looking at my list here, here's a sequence 3, 6, 12, 12. Oops, that's supposed to be 24. I apologize for that. So if I have 3, 6, 12, 24, 3 is the term, and it is my first term. 2 is a term, and it's my second term. 12 is a term, and it's my third term, because it's the third one in the sequence. And so we can write this out in this method. So we create a table where it goes 3, 6, 12, 24, and this is my first term, my second term, my third term, my fourth term. And we can find a relationship between the number in the list, or the term number, and the term itself. So when we're looking at this 3, 6, 12, 24, there's a relationship to the numbers where we multiply each previous one by a number, and that number is called our R. So in this case, we times by 2 each time to get to the next number. And so that 2 then becomes our R. R is also known as a common ratio. So what's the common ratio? And why it's called a common ratio is because I could take any term and divide by the previous one to get the R. So 24 divided by 12 gives me that R of 2. Or I could take 6 and divide by its previous term 3, and I get that R, which is 2. And that will always occur with these geometric sequences. So now what we're going to do is we're going to look at these geometric sequences, and we're going to identify R, and then we're going to use that idea to find the next 3 terms in the sequence. So here we've got 2 options. I can look at, okay, what do I times by each time to get to the next number? So each time I times by 4 to get R. Or if I can't tell, I take one number and divide by the previous number, which will tell me that my R is 4. So either option I have is good. Once I know my R, then I could find the next 3 terms. So my next term is going to be 64 times 4, which is 256. And I got to find the next one. So now I'm going to times that by 4, which is going to give me 1024. And then I times that by 4, which is 4096. And so you can tell that these numbers get big quickly. And that's why it's called exponential, is that they start off with the smaller differences, but because I keep multiplying, it gets bigger and bigger and bigger. So next one, what do I times by each time? If you don't know, just pick one number, 300, and divide by the previous number, 30. So we get 30 divided by 3, which is 10. So our R is 10. And now I'm going to use that to find the next 3 values, which really, when I times by 10, it's just adding another 0 on the end. So if I have 3,000, I'm going to add another 0 on there, which is going to give me 30,000. And then the next one, I'm going to add another 0, so 300,000. And then I'm going to add another 0, which is going to give me 3 million. And I'm easily running into the next problem. But you get the idea. Here's my R, next one, the sequence. So on the next one, again, if we don't know, I'm just going to take any number, divide it by the previous. So negative 10 divided by 5 gives me my r of negative 2. So each time I times by negative 2, so negative 40 times negative 2 gives me 80. 80 times negative 2 gives me negative 160. Times by negative 2 gives me positive 320. So when you see this alternating between positive and negative, that means our r is negative. Okay, so the next one's a little bit trickier. So now I'm going smaller and smaller and smaller because I start at 9 and then I go 3 and then negative 1 and then 1/3. So if I don't know, take any number, divide it by the previous. So 3 divided by negative 9 will give me my r, and r is really negative 1/3. So now I'm going to use that to find the next number. So if I need to, negative 1/9 times negative 1/3 gives me positive 1/27. Okay? 1 over 27 times negative 1/3 gives me negative 1 over, I gotta figure out what 27 times 3 is. 81. And then I need one more, so negative 1 over 81 times negative 1/3. So now I gotta figure out 81 times 3. 243, so this is now positive 1 over 243. So again, same idea, gets a little bit more complicated, but the process is the same. So if you could do the process with the easy stuff, it makes the harder stuff even better. So let's move on to our next one. 512, 384, I have no idea, so I'm going to take 384 and divide by 512. So 384 divided by 512. Oops, 384 divided by 512 gives me 0.75. So this is really, r is 0.75, or I could treat it like a fraction, 3/4. Either way, we're okay because they really mean the same thing. So how do I find the next number? Well, I'm going to take the 288. And I'm going to times by 0.75. So 288 times by 0.75 gives me 216. And I'm going to times that by 0.75, which gives me 162. And then I times by 0.75, which gives me 121.5. So you can easily see where in this section we're going to need a calculator to help us just make those calculations. Our brains know the pattern, and sometimes we don't need calculators, but sometimes we do. So always a good idea that in Chapter 9 we're bringing a calculator to work with. Okay, so now that we've looked at the patterns, we've found our common ratio, we're able to find the next numbers. Well, what happens if I want to find the 200th number in the sequence? Am I really going to go through and times by r 200 times to figure out that number? No. So now we have a way to write a rule for what happens that allows us to calculate the 100th term or the 200th term without having to calculate that many numbers. So what's the function rule? What's our rule for figuring it out? And any term is going to be an. So if it's my 4th term, it's going to be a sub 4. If it's my 5th term, it's going to be a sub 5. So I can figure out any term by taking our very first term, and that's what a1 is our very first term, and timesing it by r, which is that common ratio. We already talked about how to find that common ratio, to the power of n minus 1. So if I want my 5th term, this would be r to the 5 minus 1, so just 4th power. And that's what we're going to do to figure out that rule every single time. So, for example, we're going to write the function rule if our first term is 500 and r is 0.2. So I'm going to take that any term will be equal to 500 times my ratio to the n minus 1 power. And there's my function rule. And if you can write that function rule, you can find any term. So now What happens if I want to find the 10th term? Well, that means n is equal to 10. So I want to find my 10th term, which will be 500 times 0.2 to the 10 minus 1 power, or really to the 9th power. So this is really 500. Let me fix that, 500. That 5 doesn't look right. So 500 times 0.2 to the 9th power. Now, how do we calculate this on the calculator? Well, the first thing we do is we're going to calculate 0.2 to the 9th power. Most calculators have the ability to do multiple powers. So what you're going to look for is you're going to type in 0.2, and then you're going to look for a button that looks like that. That's the power button, and it allows you to assign a power. So we're going to do 0.2, we're going to hit the power button, and then type 9 and enter. And so what we're going to have now is 500 times this value. Now my calculator does scientific notation, so my calculator has 5.12 e negative 7. And so what this really is 5.12 times 10 to the negative 7th power. Some of your calculators will go ahead and put in decimal form, but that's okay. Now my calculator allows me to hit times, which will take my answer in times by 500. Which gives me my answer of 0.000256. And that is our 10th term. Okay, so let's look at another problem, because the more you see, the better it gets. We're going to write a function rule. Our first term is 5. So any term is equal to our first term times our r to the n minus 1 power. So now if I want to find the 6th term, then I'm going to go a6, so that's my 6th term, equals 5 times 2 to the 6 minus 1, or 5th power. So when I'm calculating, I do exponents first. So I'm going to do 2, and I'm going to do that little arrow. So don't forget this is 2 arrow 5. So 2 to the 5th power, which is 32. So this becomes 5 times 32. And I'll go ahead and times by that 5, which tells me that my 6th number will be 160. So just being able to write that rule saves us a lot more work in the long run. Okay, so continuing on with the idea, what is the 9th term of the geometric sequence? Okay, so now this is looking a little bit different, but it's not so bad, because I could tell right here, this is my first term, this is my a1. So when I write my rule, an equals my a1, so 2 times, now I'm going to figure out what do I times by each time. Doom, boom, boom. And if I don't know, I'm going to take any two numbers. So I'm going to take negative 6, I'm going to divide by the previous number in the sequence, which tells me that my r is negative 3. So this is going to be negative 3 to the n minus 1 power. So now I've written out my rule. I now have to figure out, well, what term do I want to find? Well, I want to find that 9th term. So now I'm going to go ahead, I'm going to plug in 9. So a to the 9th, so my 9th term is going to be 2 times negative 3 to the 9 minus 1 power, which is 2 times negative 3 to the 8th power. And now I'm going to calculate that negative 3 to the 8th power, which is positive. Why? Because anytime we have an even power, we're going to have an even number of negatives, which means they end up positive, because negative times negative is positive. So this becomes 2 times 6,561. And now I times by that 2, which tells me that my 9th term will be 13,122. So these are geometric sequences looking at patterns of numbers, which is really just exponential functions. And you'll see that relationship as we go on through the chapter. So let's look at another problem. We have the 8th term of a sequence. So my first term is 1,000. So AN equals 1,000. And now I have to figure out my R. So what do I times by each time? And if I don't know, I take any number, 125, and I divide by the previous number, 250, and I calculate that. And this is going to be my R. And when I calculate on the calculator, I get 0.5. So this is 0.5 to the n minus 1 power. Well, now I want to calculate the 8th term. So I'm going to find A8, which is 1,000 times 0.5 to the 8 minus 1, which is really just the 7th power. So now I'm going to take my calculator, I'm going to do 0.5 to the 7th power, really, really small number. So now I get 1,000 times 0.007825. And now I'm going to times by 1,000. And this gives me 7.8125. And that is my 8th term in the sequence. Not so bad, huh? Well, now let's start looking at it from a physics point of view. So now we're dropping a ball from a tower. And then we're measuring the height that the ball bounces on each bounce. So my first bounce, it bounces up 300 inches. And then the next bounce 150 inches. And the next bounce 75 inches. What is the height of the 6th bounce going to be? So the same thing, just now a problem that gives us a context, like where in the world would you actually use this? Oh, I don't know, maybe science class in physics. So AN is equal to my first term times my R. Well, what's my R? So let's take any number in the sequence. I'm going to take 75 and divide by the number before that in the sequence. And when I divide that on my calculator, I get 0.5. So my R is 0.5 to the n minus 1 power. And now we want to know the height of that 6th bounce. So we're going to find A6, which will be 300 times 0.5 to the 6 minus 1, so the 5th power. So now I'm going to do 0.5 to the 5th power. So this is now 300 times 0.03125, because I calculated this first, because order of operations says I calculate exponents first, and then I'm going to times by 300, which means that this is really going to bounce 9.375. Whatever our unit of measurement is, I happen to know that this unit of measurement is inches. And that's it. So let's look at the next problem. Again, very similar. A car's value after it is purchased form the geometric sequence of 10,000, 8,000, 6,400. How much will the car be worth in the 10th year? So very realistic, very common in car value is that we lose a lot of money in the first couple years, and then the amount of loss just kind of levels out. So it gets smaller and smaller each time. We call this an exponential decay because the values are getting smaller throughout time, and then those values, as they get smaller, the differences get even smaller. So let's go ahead and write our thing. So any term AN will be equal to my first term, 10,000, times R. So let's figure out, I'm going to take any value and divide it by the one before it. So R equals 8,000, 1, 2, 3, divided by 10,000, 1, 2. And I'm going to cancel out some zeros so I know what I'm dealing with. So this is really 8 over 10. If I divide that in my calculator, I'm going to get 0.4. No, 0.8. Sorry. That makes more sense. 0.8. So 8/10, 0.8. So this is 0.8. And this is the n minus 1 power. So now if I want it for the 10th year, in the 10th year, it will be 10,000 times 0.8 to the 9th power, because I subtract 1. So now I'm going to take the calculator, 0.8 to the 9th power. And I'm going to times that 10,000 by, and this is a really long decimal, 0.1342177. You want to be careful about rounding too quickly, because then your error may translate into quite a bit of a difference. So 10,000, which gives me $1,342.18. And I rounded here appropriately because when we start talking about money, it's appropriate to only have 2 decimal places. So what happens if you would have rounded this to 0.13? Then your answer would have been 1,300, which there is a big difference. And if you're trying to sell your car, which value would you really want? Well, I definitely want the more money. That extra $42 can buy me quite a bit of pizza. So it's worth it to me. So keep in mind that when you're rounding, it can be good and it can be bad. And in this case, not so good. So the more we don't round, the more exact our answers are, and the better off it is for us in the long run. Okay, that's it for 9.1.